Last episode replaced Kestrel's VPN with something that verifies every remote connection instead of trusting a network tunnel. That closed one edge. It didn't touch the edge that's actually grown fastest over the last couple of years, the API layer. Every mobile app Kestrel ships, every partner integration with a hospital system or an insurance payer, every internal service calling another service, all of it is an API now, and the count of those APIs has been climbing far faster than anyone's ability to keep an accurate list of what's actually running, let alone secure each one properly. Here's the version of that problem that actually happened at Kestrel. A patient portal endpoint that checked whether you were logged in and never once checked whether the medical record you were asking for was yours. Change one number in a URL and it handed over somebody else's chart. That's not an exotic attack. It's the single most common finding in API security audits anywhere, and it's where we're spending most of this episode. Every security framework built for the web assumes a particular shape, a browser, a human clicking around, and a server rendering pages for that human to look at. That shape barely describes how modern systems actually talk to each other anymore. A single patient portal screen at Kestrel might call 5 or 6 separate backend APIs just to render one page. Appointment data from one service, billing status from another, lab results from a third. And none of those calls involve a human typing anything into a form. They're machine-to-machine, structured, and entirely predictable in shape, which is exactly what makes them attractive to attack in a way a rendered web page usually isn't. 3 things are true about APIs specifically that aren't equally true of a general web application. First, every microservice decomposition, every mobile app, and every partner integration adds at least one new API surface, often many, and that number only grows over time. Nobody decommissions an API as often as they stand up a new one. Second, an API is built to be consumed by code, not read by a person, which means an attacker doesn't need to click through a UI to find the interesting requests. They can read the API's own documentation, or its schema, or just its URL structure, and script a request straight at the exact endpoint that matters, at whatever volume they choose. Third, and this is the part that catches most teams off guard, an API's security is disproportionately about its business logic rather than its markup or its scripts. There's no HTML to sanitize wrong, no client-side script to inject. What's actually at stake is whether the server-side logic behind a call correctly checks who's asking and what they're allowed to touch. And that check either exists or it doesn't. On every single endpoint, all of them equally reachable. Put those 3 things together and the picture is a genuinely different attack surface, growing faster than most teams' ability to even produce an accurate list of what's live, which is exactly the sprawl problem the next scene walks through, before we get to what actually goes wrong. Kestrel's own API surface is a useful illustration of exactly how this happens, because nothing about how it grew was reckless. Start with the partner integrations from a few episodes back. Every hospital system partner and every insurance payer partner federates in through the identity broker, then talks to Kestrel's platform through a set of partner-facing APIs, and Kestrel now has partners in the double digits, each with its own integration surface. Layer on top of that, the internal picture, dozens of internal services, now mesh enforced with mutual TLS from the Istio rollout, a few episodes back, calling each other constantly. Each call technically an API, even though no partner or external client ever sees it. Add the patient-facing side, a web portal and a mobile app, both backed by their own API layer, plus an administrative API surface, that Kestrel's own staff now reach remotely through the identity-aware access that replaced the VPN last episode. None of that sounds unreasonable in isolation. Each addition was a deliberate, well-reasoned architecture decision made by a team solving a real problem in front of them. The sprawl isn't a failure of any one decision. It's what happens when dozens of individually sound decisions accumulate without anyone owning the resulting total. Kestrel's identity architecture is genuinely solid at this point. OIDC tokens, workload identity between services, MTLS, everywhere internal traffic flows. But knowing exactly who's calling an API reliably is a completely different problem from knowing what that caller should be allowed to do once they've proven who they are on this specific request against this specific piece of data. That second problem is where this episode actually lives. Picture Kestrel's API surface the way an architecture diagram actually draws it. Every partner integration, every mobile client, every internal caller, all funneling through a single layer before any request reaches an actual service. That layer is the API gateway, and its value isn't that it does anything exotic. It's that it sits at exactly one choke point through which every API request must pass, which means whatever gets enforced, that gets enforced consistently, instead of getting re-implemented slightly differently, inside every one of Kestrel's services. 4 concerns belong at that choke point specifically. Rate limiting, so no single caller can overwhelm a backend service or run up cost by hammering an expensive endpoint. Enforced once at the edge, rather than left to each service to remember. Authentication and authorization delegation. The gateway validates the OIDC-issued token from the identity layer a few episodes back, confirming who's calling, and for anything requiring a finer-grained decision, then, is this token valid? It calls out to the policy decision point built on Open Policy Agent, covered a few episodes back, rather than every service re-implementing its own authorization logic from scratch, schema and contract validation, checking that an incoming request actually matches the API's defined shape before it ever reaches application code, which quietly closes off a wide category of malformed or malicious input before a service has to think about it at all. And centralized logging. Every request, every caller identity, every response code captured in one place instead of scattered across however many services happen to log in, however many different formats. None of this makes any individual service correct on its own. It makes the enforcement of these 4 specific concerns consistent across all of them, which is precisely the property Kestrel's internal architecture lacked before the gateway existed. 5 different teams, 5 different half-built rate limiters, none of them quite matching. There's a dedicated project for exactly this problem, the OWASP API Security project, maintained separately from the classic OWASP Top 10 that covers general web application vulnerabilities. That separation exists for a reason. Cross-site scripting and SQL injection still show up in APIs, but they're not what dominates real API security findings. What dominates is a different, more specific failure, authorization logic that's missing, incomplete, or checks the wrong thing over and over across a handful of recognizable categories. You don't need this episode to recite whichever exact ranking the current list happens to publish, because the order shifts slightly between revisions and memorizing a ranking is the wrong skill anyway. What matters is recognizing the categories themselves deeply because they recur constantly across real API estates regardless of which number they're assigned. We're covering 8 of them here, the ones that show up hardest and most often in practice, starting with the one that causes more real damage than the rest of the list combined. broken object level authorization, usually shortened to BOLA, and closely related to what's long been called an insecure direct object reference, or IDOR. Here's the exact shape of the flaw, and it's almost insultingly simple once you see it stated plainly. An API checks that the caller is authenticated. Yes, this is a real, logged-in user holding a valid token, but never checks that this specific caller is authorized for this specific object being requested. Call an endpoint like /API/orders/122345, and if the service verifies you're logged in, and then just fetches order 122345, without asking whether order 122345 actually belongs to you, changing that number to 122346 hands you someone else's order. No exploit, no injected payload, nothing a web application firewall is likely to flag. Just a number, incremented. This is the single most common finding in real API security assessments, and the most damaging for a structural reason. It's invisible to every layer that isn't the specific service holding the data. The gateway can confirm the token is valid. The mesh can confirm the request arrived over an authenticated, encrypted channel. The policy engine can confirm the caller's role permits calling this endpoint at all. Every one of those checks can pass cleanly, every time, on a request that's still fundamentally illegitimate, because none of them know what belongs to whom. Only the service holding the actual data does. Kestrel found exactly this shape of flaw in its own patient portal API. A GET request against a patient's medical record, addressed by a patient ID directly in the path. The endpoint's authentication was fine. It required a valid OIDC token, checked cleanly by the gateway, exactly the way the identity arc a few episodes back intended. The problem was one layer deeper. The patient portal service took the patient ID out of the URL and queried the record store directly, without ever comparing that ID against the identity carried inside the caller's own token. Any authenticated patient, logged into their own account correctly, could request any other patient's record just by changing the ID in the request, and the service would hand it over without complaint. It surfaced because the gateway's centralized logging, the fourth of the 4 concerns from the last scene, caught something worth a second look. A single authenticated session, generating a tight, fast sequence of requests against sequential-looking record IDs, a pattern far more consistent with someone probing than with a patient looking up their own chart. A security engineer pulled the thread, found the missing check, and confirmed nobody's data had actually been exposed at scale before the fix landed. The fix itself lived entirely inside the patient portal service. One added piece of logic comparing the patient ID in the request against the patient ID carried in the caller's own verified token claims, rejecting the request outright on any mismatch. The gateway didn't write that check, and it couldn't have. It doesn't know what a patient record is or who owns which one. It only knows whether a token is valid. That distinction is the single most important architectural idea in this entire episode, and we're coming back to it directly in a few minutes. Broken authentication, the second category, covers a cluster of failures in how an API verifies identity in the first place, before authorization ever becomes the question. Concretely, API keys used as the only credential, often long-lived, sometimes checked into a repository, or shared informally between teams, the way scheduling and billing shared implicit trust back in the Stride episode. Tokens accepted without proper signature validation, or validated against a weak algorithm, letting a forged token through. Login endpoints with no protection against repeated automated guessing, letting an attacker simply try credentials until one works. Password reset flows that leak whether an account exists at all through a slightly different error message. Everything the identity arc covered earlier in the season is the direct answer to this category. Short-lived, properly validated OIDC tokens instead of static API keys, rate-limited authentication endpoints so credential stuffing doesn't scale, and phishing-resistant methods for anything reaching a genuinely sensitive endpoint. Kestrel's identity rebuild already closes most of this category off by construction, which is exactly the point of building it once, correctly, rather than leaving every new API to reinvent its own login logic. Broken object property level. Authorization is a close cousin of BOLA, one level down. Instead of the wrong object, it's the wrong fields inside the right object. The classic shape is excessive data exposure, an endpoint that returns an entire patient record object because that was the easiest thing for the service to build when the calling screen only ever needed a name and an appointment time. Every other field on that object, insurance details, billing history, clinical notes, travels over the wire regardless. And the only thing standing between a curious or malicious caller and the rest of that data is whether the client application happens to display it. That's not a security control. That's an accident of which fields a particular screen happens to render. The same category runs the other direction too, on writes rather than reads, sometimes called mess assignment. An endpoint that accepts a whole object from the caller and blindly saves whatever fields arrive, rather than an explicit list of which fields this particular caller is allowed to set. Send a field the API never intended to expose for editing, an account role, a discount flag, a permission level. And if the service isn't filtering incoming fields explicitly, that field gets written right along with the legitimate ones. The fix on both sides is the same discipline. Define exactly which fields a given caller can read and which fields they can write, explicitly per endpoint, rather than serializing or deserializing whatever the underlying object happens to contain. Unrestricted resource consumption is the category that shows up as a bill or an outage rather than a data leak, and it covers any API that never bounds how much of anything a single caller can consume. No rate limit on calls per minute. No cap on how large a request payload can be. No limit on how many records a single query can return, or how deep a nested query can recurse before something finally errors out. Every one of those gaps turns an ordinary API call into either a cost-based attack, running up cloud compute, or third-party API charges by hammering an expensive endpoint at volume, or an availability-based attack, exhausting a backend service's capacity until legitimate callers simply can't get a response. This is the category where the gateway earns its keep most directly, because rate limiting is precisely a cross-cutting concern that belongs enforced once at the edge rather than re-implemented per service. A token bucket or sliding window limiter at the gateway, scoped per caller identity rather than per IP address, catches this cleanly, regardless of which service sits behind it. Pagination enforcement, maximum payload sizes, and query complexity limits belong at the same layer for the same reason. Every service would otherwise need to remember to build these protections itself, and at Kestrel's scale, at least one of them always forgets. Broken function-level authorization is BOLA's sibling at the level of the endpoint itself rather than the object behind it. The API correctly confirms the caller is authenticated and then lets the caller reach the wrong function entirely, because nobody checked whether this specific caller's role actually permits reaching this specific endpoint. A regular patient portal user holding a perfectly valid token discovers that an administrative endpoint, one meant only for Kestrel's internal support staff, responds normally to their request too, because the endpoint checked for a valid token and stopped there, without asking whether a valid token from a patient role should ever reach an admin-only function in the first place. This flaw hides especially well in APIs that were never meant to be discovered casually. An internal admin endpoint nobody bothered documenting publicly, on the reasonable-sounding assumption that if nobody knows the URL, nobody will call it. That assumption fails constantly because URLs leak through a mobile app's compiled code, through a misconfigured API documentation endpoint left open, through simple guessing based on naming conventions the rest of the API already reveals. The actual fix is the same policy decision point pattern from a few episodes back. Every function level check should run through the same centralized authorization logic as everything else, rather than depending on an endpoint staying undiscovered. 3 more categories round out today's list, and each earns its place for a different reason. Server-side request forgery happens when an API accepts a URL or a similar reference from a caller and then fetches it itself, server-side, without restricting where that fetch is allowed to go. An attacker who can influence that URL can potentially point Kestrel's own server at its own internal network. A metadata endpoint, an internal admin service never meant to be reachable from outside, using the API's own server as the thing making the request, which sails straight past network controls, built to stop external traffic, because the request never looks external at all. Security misconfiguration is the broadest category by far, and the least glamorous. Overly permissive cross-origin resource sharing settings, verbose error messages that hand an attacker a stack trace and a library version for free, default credentials never rotated out, unnecessary HTTP methods left enabled on an endpoint that only ever needed one of them. None of these are exotic. All of them show up constantly, because a misconfiguration doesn't require anyone to make an active mistake. It just requires nobody actively fixing a default. And improper inventory management is the category that connects directly back to the sprawl scene from earlier in this episode. Old API versions left running long after the client that used them moved on. Undocumented endpoints nobody remembers building. Staging environments quietly exposed the same way production is. Kestrel's own history here isn't clean. An old /v1/endpoint from an early partner integration stayed live for months after every real client had already moved to v2, unmonitored, unpatched, and functionally invisible to anyone doing a routine review, because it wasn't on the list of things being reviewed at all. An API you don't know exists is an API you can't possibly have secured, no matter how good every other control on this list happens to be. Here's the architectural point this entire episode has been building toward, and it's worth stating as plainly as possible. The gateway centralizes enforcement. It does not centralize authorization logic for every possible object in the system, and conflating those two things is exactly how an organization ends up believing it's protected against BOLA when it isn't. Look back at everything the gateway legitimately owns. Validating that a token is real, confirming the caller's role permits calling this class of endpoint at all, rate limiting how often any of that happens, checking that a request matches its expected schema, logging all of it centrally. Every one of those checks is genuinely valuable, and every one of them is something that should live at exactly one place rather than get re-implemented per service. But none of them can answer the question that actually mattered in Kestrel's patient portal flaw. Does this specific, fully authenticated, fully authorized to call this endpoint caller actually own or have a legitimate right to this specific record? That's a business logic question, and answering it requires knowing what a patient record is, who it belongs to, and how ownership is represented in the data itself. Knowledge that lives inside the service that owns that data, not at an edge component sitting in front of dozens of unrelated services that each have their own idea of what an object even is. This is why BOLA remains the most common finding in API security assessments, even at organizations running a genuinely well-built gateway. The gateway was never going to catch it, because catching it was never a gateway problem. Every service still has to own its own object-level authorization on every endpoint that returns or modifies a specific record, and no amount of edge enforcement substitutes for that discipline living exactly where the data does. 3 mistakes recur constantly here. First, treating the gateway's existence as proof the API layer is secure, when what the gateway actually guarantees is that a handful of specific, cross-cutting concerns are enforced consistently. A real and valuable guarantee that says nothing at all about whether any individual service checks object-level ownership correctly. Second, testing APIs the way teams test web applications, running a scanner built to catch cross-site scripting and injection, and calling the API secure when it comes back clean, without ever specifically testing whether changing an ID in a request returns data that shouldn't belong to the caller. BOLA doesn't look like a vulnerability to a generic scanner. It looks like a perfectly formed, successful request, and only manual, authorization-specific testing reliably catches it. And third, letting inventory drift the way Kestrel's old v1 endpoint did, standing up new API versions freely, and never building the corresponding discipline of decommissioning what the new version replaced. An API estate that only grows, never prunes, guarantees that improper inventory management stays a live risk indefinitely, regardless of how well every newly built endpoint happens to be secured. Everything in this episode has been about what an API tells you when you ask it the right question, and about a gateway that enforces the questions worth asking consistently. There's a different, quieter problem sitting underneath all of it. What's actually happening inside a running service, at the process and kernel level, regardless of what any API, any logline, or any application even chooses to report about itself. Next episode, we get underneath the application entirely. eBPF runtime security with Cilium and Falco. Observing what the app won't tell you straight from the kernel up. If you're building systems that need to survive an estate, nobody can fully inventory by hand, not just look secure on an architecture diagram. Subscribe, and I'll see you in the next one.